A rigid body is an object that can't be deformed. Rigid body dynamics describes how systems of rigid bodies behave and how forces can produce motion. First, let's think about how we would represent a 2D rigid body in a program. We can think about a rigid body as a collection of point masses. At each point in time, we'll need to store the position of the body, and to make it move, we'll need to know its velocity and acceleration. If we know all the forces that apply to the body, Newton's laws of physics tell us how it will move. The rate of change of the position is velocity, and the rate of change of velocity is acceleration. A body like this can also rotate. Even if it isn't moving, we need to store its orientation as a rotation. What point does it rotate around? Well, it makes calculations easier if the center of the model is its center of mass, which we can compute by taking a weighted average of its constituent point masses. The center of mass is a natural choice for the axis of rotation because any pure torque around that axis exerts no net force on the body. The way we move the body is by applying force, which adds velocity. Velocity isn't necessarily constant, but changes as the body evolves. How it changes is linked to its acceleration at a given point in time. The last thing we need to model the movement of a rigid body is how it's spinning. This is called angular velocity. Like with acceleration, we'll store something called angular acceleration, which can be calculated from the magnitude, direction, and point of application of forces on the body. We also need to get the object's moment of inertia, which we can think of as angular mass. We can calculate the object's moment of inertia by its mass weighted by the distance from the center of mass squared. For instance, we can sum up the moments over the point masses composing the object. These quantities give us everything we need to simulate a rigid body. Now that we know how to model a rigid body, how do we make it move? We add forces. First, how does the object accelerate? Well, remember, force equals mass times acceleration. All we have to do is add all the forces applied to all the points to get the net force on the body, and then divide by the total mass to get acceleration. How about angular acceleration? Well, an analogous law applies. Every time a force is applied to a point not in line with the center of mass, it also produces a torque, which can be calculated using the cross product, torque equals r cross f. In the torque equation, r is the vector from the center of mass to the point of application of the force. We can think of torque as force with its effect relative to its distance to the rotational axis factored in. Just like with forces, we can combine all the torques to get a net torque. We've already mentioned that the object rotates only around its center of mass. Imagine applying a force to an object with a fixed rotational axis. We get the most torque when our force application vector is perpendicular to r, and no torque when the vectors are parallel. Now suppose we want to put all this together in a simulation. First, consider what information we have at a given point in time. Based on the effects of gravity and other rigid bodies, various forces are being applied to our object. That's the only external information we need to consider. Everything else about our object follows from the constant evolution of its state. In particular, between two adjacent points in time, the position changes proportional to the velocity, and the velocity changes proportional to the acceleration. The same is true for rotation, angular velocity, and angular acceleration. But how do we actually do these calculations? The answer is that it's too difficult to exactly determine the motion of our rigid body, because this might require solving a differential equation with a force function that might not even have a closed form expression. The next best option is approximation. Instead of doing exact calculations, let's set a small time frame we'll call delta t. This delta t is the time step of our physics system. We'll do what was explained earlier, where position and velocity are updated every time step based on the previous values of velocity and acceleration. The Euler method provides update equations we can use to iterate our object's position, velocity, rotation, and angular velocity. Suppose we threw our rigid body into the air. Here's the true motion of the center of mass as it travels in a parabola under gravity. Let's see what happens as we change delta t. Notice how, as we decrease delta t, the simulated trajectory matches the exact one more precisely, but we also have more dots, which means more calculations needed. This is the simulation trade-off. The lower the delta t, the more precise the simulation is, but at the cost of taking longer to compute. The examples so far have been for 2D rigid bodies, but 3D rigid bodies can essentially work with the same update equations. Position, velocity, and acceleration will be 3D vectors instead of 2D vectors. Angular velocity and torque will be 3D vectors instead of scalars, where the direction of rotation is given by the right-hand rule. We can think of the orientation as a 3x3 rotation matrix, but in practice we will use a quaternion, which removes certain edge cases and simplifies the update steps. The last thing we'll talk about is collisions. We don't want our rigid bodies to pass through each other. The math gets a lot more complicated, but all we really need to do is add more forces. If two objects collide, what really happens is that an instantaneous force is applied, which we'll call an impulse. We first employ a technique called collision detection. Then, apply the exact amount of force that would cause the object to stop in the next time frame. This force is applied once to instantaneously change the velocity. Now that the ball is resting on the platform, the system has to keep track of which points are in contact with each other. The platform exerts a constant normal force on the ball to prevent it from falling through. Finally, the points of contact affect friction. When the ball moves horizontally, the surface exerts a force in the opposite direction. This slows the ball and causes it to turn or roll. And those are the basics of rigid body simulation. We hope you enjoyed our cartoon.